So in this video, I will let you know how to verify the identification assumption of RD design. And that's very crucial for the validity of the result when you use the RD. So the key assumption of RD design is the continuity assumption. So that is no other confounding factors also change abruptly around the cutoff except for the treatment variable. So other variables should go very smooth, continuous across the cutoff. So if that, you should expect there's no jump in other covariates around the cutoff. And you can try to verify this by using the RD, but you just replace your outcome variable with the other covariates and run the same RD estimation to see whether there's any discontinuity for these covariates. Okay, but if you find the covariates actually jump at cutoff, we might adopt the identification assumption of RD design. So that is maybe the continuous assumption may not hold. So if that's, you might not be able to implement this design. But another solution is you just include this covariate when you run the regression for your RD estimation. That's another possibility. And you also need to examine the discontinuity in density of assignment variable to also make sure all the confounding factor, all the variable around the cutoff will be very similar. So if individual can manipulate their assignment variable, that will also invalidate the continuity assumption, because they can strategically manipulate their assignment variable to above or below the cutoff. That means people can select to get a treatment or not to get a treatment. And that will create a selection bias. And the point of RD design is people actually, around the cutoff, people cannot really control whether they can above the cutoff or below the cutoff. So that will make people are very similar. If you compare two groups of people that are just above or just below the cutoff, they will be very similar. They are very comparable. But if they can choose whether they can pass the cutoff or just below the cutoff, that will make the people just above or just below the cutoff are no longer comparable. So in that case, that will generate a selection bias. Okay. So here I give you one example to show what happens if people can choose whether they can above cutoff or below cutoff. So suppose there's an individual called C, and originally it's at this position. So y-axis is the outcome variable. Horizontal axis is your assignment variable. So the cutoff is 2. And C is right below the 2 originally. But so you will get the effect is the called BA. BA is the effect. Is the discontinuity. Okay. But what if they can change whether they are staying below the cutoff and above the cutoff? If the C change to the C plum, that will make your RD estimation be changed. Because now C plum actually, the position here actually is increase the outcome, average outcome right after the cutoff. So the estimate for this intersect will become B plum, a big increase, because C plum is bigger than the average outcome for the people who right after the cutoff. And C, the individual C actually their outcome also above or more than the average outcome for the people right below the cutoff, that if he move to this place, that will make the intercept estimate will become A plumb, will decrease, because these guys on average their outcomes more than the people who are around here. Okay, so if individual C change to the C plumb, actually it will make the discontinuity estimate become the B plumb, A plumb, and that will make the discontinuity estimate become bigger if the individual C can change his position to C plumb. That will bias our estimate. So the intuition is, if people can choose whether they can just below cutoff or above cutoff, that will make people around the cutoff are not comparable, because whether they can get a treatment or not now is they select their decision. Okay. So if such thing happen, you will expect a lot of individual might just stay around the cutoff, either just below the cutoff or just above cutoff. So if such thing happens, such so-called sorting behavior happen, we might find we should be observed there's discontinuity in the distribution of the X at cutoff. That is the density or frequency of specific interval of your assignment variable might be show abnormal. You will see a lot of people right or just below the cutoff. So you will find that there's a bunching to the right or to the left of the cutoff. Okay, so here I give you one example to show such thing actually can happen in the real life. This paper tried to show this manipulation of the social program eligibility. So they use the example in the Colombia. They will give someone's cash transfer if they use the poverty index. If this they below some threshold of poverty index, they will receive the cash transfer. If they just above this cutoff, they will receive nothing. So they cannot receive this cash transfer. So maybe you want to know the effect of the receiving the cash transfer on the labor supply, and you want to use RD, and you can use the poverty index as a rounding variable to determine who can get the cash transfer, who cannot. That's a good RD design. But this RD design will be valid given people cannot manipulate their poverty index. And this paper tried to show there's evidence suggests people actually can manipulate. And why is because government basically release how they calculate this poverty index after 1997. So before 1997, no one really know how the government determined their poverty index, the algorithm to create the poverty index. But after 1997, people know that, so they will manipulate this to make they can receive the cash transfer. Okay, so here is the example. That's what I mean. We should examine whether there's any discontinuity in the distribution of your poverty, your assignment variable. So the y-axis is the share of the sample of the individual located in the specific interval of the poverty index score. Okay, and you can see before 1997, 1994, 1995, the number of the individual located in the specific interval of the poverty index actually is quite smooth. And there's no spatial thing happen around the cutoff. So red line indicator cutoff. So right below the cutoff, you can receive the cash transfer. But people actually, before 1997, they don't know how the government calculate this. So there is no manipulation. But after 1997, people know how to calculate this. So you can see in 1998, actually, a lot of people bunch around the cutoff, right below the cutoff, to make sure they can receive the cash transfer. In 1999 also, 2000, 2001. So when this thing happened, you cannot really use the property index or as a running variable and this cutoff to examine the effect of the cash transfer on the labor supply, because people can manipulate the assignment variable. So in that case, only those who want to receive the cash transfer, they will try to make they can below the cutoff. And these people, maybe they have very different characteristics compared to the people who right above the cutoff. For example, they might be lazy, or they just want to stay at home. They don't want to go earn money. That's why they have very strong incentive to receive the cash transfer. So in that case, the two groups of people around the cutoff are no longer comparable. Okay. So in that case, you cannot use the RDD sign to examine the causal effect. Okay. So how to examine the discontinuity in density of the assignment variable? So first things is you just plot the distribution. So like this, to know whether there's any discontinuity in the distribution of the assignment variable around the cutoff. If you find such thing happen, that potentially suggests there's some manipulation around cutoff, around your assignment variable. And you can also formally test it by doing the following step. The first step is you need to partition the assignment variable into several intervals and calculate the frequency, the number of observations in each interval, in each bins. So like this, calculate each interval, how many individuals stay in that interval. And then you also need to make sure each interval does not overlap, and also especially cannot overlap the cutoff, to make sure all the interval either are above cutoff or below the cutoff. And then you basically run the two local linear regression, run the RD estimation, but now you use the outcome is the number of observations as the outcome. Or take a look. You can take a look of a number of observations for each interval as the outcome. And you want to know whether these two groups, whether the number of observations just above cutoff or just below cutoff, they have any significant difference or not. Okay, so you might run generate this graph and try to test whether there's any discontinuity in terms of your frequency, the number of observations in each interval, to see. But for this example, there's no discontinuity, very obvious in the graph. But sometimes it has some discontinuity. For example, the example we just mentioned, you can see if you use the test, you will find very big discontinuity, because the number of observations here, right below the cutoff is this, and right above is this. So there's a discontinuity, and it's very significant. You should be fine. So you can formally test it. Basically, you just use the number of log of the number of observations as the outcome and run the RD, and you will get a result to see whether your RD estimate is significantly different from 0 or not. Okay, so that's for this part of the video. Thanks.